Yeah. So my name is Ido Kaminer. I'm from Technion, and I'm actually it's a great honor to get an opportunity to come to this conference and participate. I'm really grateful for this. Actually, my only problem with the conference is that I have to speak right after Seth Lloyd, who gave this super inspiring talk, and so I'll try to give it a fight and present some wild ideas and some interesting concepts. So a few things that I want to tell you about today. This is a new approach. I want to basically propose a concept, a very practical one, for how we can try to approach quantum gravity, building on recent advances on computational tools that were developed in the last year and a half, 2 years, by several groups, and give us an ability to try to tackle challenges in quantum gravity. And this is a joint work with my student, Alan Malin, who was here actually, in the audience as well, also enjoying this conference a lot. And it came up from brainstorming sessions and discussions with different people, like Yaron Fadad, who's presenting today, and Eli Cohen, who will join us later today. But I think before I delve into more of this, I want to say a few words about my background, because I'm you can say a theoretical physicist turned experimentalist, or maybe the other way around. And I have this picture here. I don't know if everyone here is familiar with this. This is an electron microscope. This is how we get the images of COVID. And what my lab does is we modify those electron microscopes by putting laser pulses in, so we can study fundamental physics of the interaction between electrons and photons, and look into the soft belly of QED. And this is probably today the most heavily modified electron microscope in the world, in the sense that we can look into individual photons being absorbed or emitted by an electron, ask ourselves whether this electron collapses when it's interacting with a single photon, maybe partially collapses. So we can do some pretty cool things with this. I'll start by showing you a few things that we can do with electron microscopes, because I think they can give a little bit of motivation for the rest of the talk. So personally, why I like doing physics with free electrons, and free electrons it's a very old field. If you go, your microwave oven is working based on free electron radiation. Free electron lasers and synchrotrons and a lot of other facilities, it's free electron radiation. We do free electron radiation, but in a weird modified ways. For example, if you take, this is called van der Waals materials, those are two-dimensional materials stacked together, and they produce natural periodicity. So the electrons flying through them will be modulated periodically by the crystalline structure, and that causes the electrons to emit X-rays, and that's currently the only way to make tunable X-ray sources on a scale that you can put in a single room and not in a billion-dollar facility. In another side, people use electron microscopes for microscopy. That's basically the name. But we can do something a little bit different. We can use electrons to image light, to get images of how light looks like. So if you think about periodic structures that can hold light, those are called photonic crystals. They are coming from the idea of atomic crystals, where electrons take those Bloch modes. So light can take Bloch modes as well. And this is a way for us to image then how Bloch modes look like. And then we can also time the interaction and then make movies. So this is an example of light waves in the infrared that are coupling into a material called hexagonal boron nitride, and then coupling with the phonons in this material. So it's a kind of hybrid phonon polariton mode. It's light and sound together. And you see, this is real data of how the actual movie looks like for electrons imaging those things. So we can do quite a lot with this old field of electrons, electron physics, but emerging now with a couple of groups around the world that are building those machines and looking into new ideas of how we can do really cool physics with it. The one side of it I like the most is actually acting back on the electron. If you want to shape the electron wave function, take individual electron wave functions and shape them. And that's something we can do today with light fields. This is an example of data we take where we look at the electron spectrum. So that's the electron energy that originally was one peak over here. It's a relatively monoenergetic electron. And after interacting with the laser, what happens to it is that it takes this hundreds, and we actually measured up to thousands of individual peaks. Here you only see a section of it. So the electron basically doesn't know anymore what its energy is. And it becomes a superposition of multiple energy peaks here, which each correspond basically to the absorption or emission of a single photon. And we can actually show that this can happen in equivalent manner. So that allows us to actually explore something pretty cool. which is what happens to this electron once it absorbs or emits a single photon? Will its wave function collapse or not? What actually happens to electron interference after it interacts with light? And here, this is an experiment from last year. This is an artistic view of the structure we made. This is actually a miniaturized accelerator made in Göttingen, Erlangen, Germany, by Peter Romanov. This group is doing fabrication on the nanoscale of silicon structures. The only thing that is not accurate about this is that it's way longer, and we can send the electron exactly through the structure precisely to interact with the electromagnetic field inside. And then we can ask, well, what happens to this electron after interacting with the field, with a very weak field? Will it collapse when absorbing or emitting a photon, or will it stay coherent? And the way to think about it is something like this. The absorption and emission is a bit like a quantum walk on the electron energy ladder. So the electron either goes up in energy or goes down in energy. And we can show that this is, for classical light, this actually goes in a coherent way. So the electron can interfere with its own paths when emitting and absorbing an individual number of photons for classical light that is interfering with it. And then the electron energy spectrum will look something like this, which shows you a lot of examples of interference and destructive interference, very complex pattern. We can match experiment and theory very precisely there. But when we change the nature of light, we can change also the way the electron behaves from doing quantum walk to doing classical random walk. And then the way the result looks like will be a Gaussian. So the electron will go like this classical drunken walker that will create this Poissonian-like, Gaussian-like distribution. And that really allows us to tune how much collapse happens in the interaction between electron and light by the nature of light itself. And I can go on about this and tell more about this, and I'm happy to discuss this more, but I want to take us to even more fundamental question in electrodynamics and try from there to propose an idea for quantum gravity. So imagine this alternative history coming from optics. Had we not known about the electron and the positron, okay, but we still had amazing lasers. So somehow we had those really intense high power lasers we have today. Would we still discover QED? And think about it for a bit. If we had only the light field, so we have Maxwell equations and lasers that are immensely intense, could we still get to this theory of QED? And I want to say yes, because once having strong enough lasers to see light by light scattering, we would start getting clues about something that has to hide in there, that has to mediate between photons. And we normally think about mediation between electrons and blame the photon on that, but it's actually also the opposite. There is an interaction between photons, right? And that interaction between photons, you can look at it like that, right? Photons has this pretty minute chance, if they're in optical frequencies, to create electron-positron pairs, right? Electron-positron pairs can then interact between themselves, and that will create this diagram of what we call light by light scattering, right? Where photons can interact. And that is something we know is possible at very high photon frequencies or at very high photon flux. And actually we expect high intensity lasers to reach that regime where we can start studying loop orders in QED with lasers pretty soon. You'll take a quick question?
Very quick. How would we know whether this is due to electrons or not fundamental nonlinear electrodynamics like Born-Infeld theory or you know, I'm just asking because you asked the question.
How do we know
experimentally, how would we know that it's due to an electron moving in a loop or fundamental nonlinear electrodynamics? Yeah. That's a question.
Yeah, where you're asking whether, basically, to what extent can we trust QED today, or whether we can get to this regime.
Because you mentioned we don't know what QED is.
It's an interesting question, right? You can argue that those experiments will not be the future, not so far in the future, high-intensity laser experiments. On the one side, they are giving us a kind of clue into high-energy physics without CERN, without accelerators. It's a completely different way of doing that. And whether this will also open up options to ask questions, well, maybe QED is wrong and there are corrections needed there, who knows? But I want to bring it for another reason, because this alternative history of having only light will look something like this. At some point, right, we have no electrons and positrons, so at some point we would discover that Maxwell's equations are nonlinear. There are nonlinear terms in Maxwell's equations, or the Lagrangian will look something like that. There will be four order terms in F, and which gives us this kind of vertex. Right? And then we'll start asking, well, is there a more fundamental theory that can explain this interaction between photons? And maybe that could be a way to find QED in this alternative history. Or as a kind of algorithm, I would say, high intensity lasers will give us the terms that look like this. And then from those terms, we could then seek out what heavy particle or particles could be integrated out at a low energy to create this effective field theory, right? This kind of thing that we call the Euler-Heisenberg-Lagrangian. Such heavy particles can then give us the full UV Lagrangian. And that's the kind of logic, or as an algorithm, let's think about, we can search over Lagrangians and try many, where low energy EFT will match the one known from experiments. Will match those kind of corrections. And then one of those Lagrangians will be QED. And then if we have too many candidates, well, then we can start arguing which one is the nicest, or we can try to find all the terms here with even more intense lasers and get additional way to exclude candidate Lagrangians. So that's the kind of idea that we could have done in this alternative history. Now, I want to try to take this kind of logic and apply it for gravity. Okay, because we have this interesting question of, can we apply this alternative history to gravity? Could the Einstein-Hilbert Lagrangian, the regular GR Lagrangian, be an EFT like the Euler-Heisenberg Lagrangian? Be an effective field theory? And the immediate answer that people sometimes give is no, but that's a wrong answer, because people say, well, Einstein's field equations are very nonlinear. There are interactions between gravity and field. There is a very strong nonlinearity in those equations, while Maxwell's equations are actually linear, and that's a big difference. But this comparison is incorrect, because if you think about high enough intensity lasers, you actually get the equations for free space electromagnetic fields are nonlinear as well, right? This is exactly the idea of the Euler-Heisenberg Lagrangian. So the Maxwell's equations, or the correct equations of electromagnetic fields in vacuum are nonlinear as well. They're not different from Einstein's in that sense. Okay, I think that's an important point, right? Just to remind myself to verify that the electromagnetic field and the gravitational field are both nonlinear, fundamentally in the same way, if you like. But one is because, well, of curvature and different phase invariance and stuff, and one for maybe a different reason, but we kind of try to tie them together for a similar reason. So our hypothesis, and that's why I want to take us through much of the talk, is that the curvature of space-time, gravity here, is the result of indirect interactions between particles in flat space. Okay, those particles could be graviton-like, right? Maybe spin too, but there will be particles in flat space, and they will be interacting. The interaction is mediated by some other heavier particle, like the electron positron in that sense, right? Like the electron positron in QED. So that's the kind of logic, and this logic is not completely new. The idea, the broader field looking into this is an emergent gravity is the broader name for that. It's a kind of emergent gravity. But what's interesting about it is that it belongs to a wider family of problems that we can now attack with recent tools that were not available even just 2 years ago. And that's something I want to talk about more now, about how to automate the calculation of a search like that, because we would like to try a lot of Lagrangians and find which ones work. So that's the proposal. We'll automate a search over candidate Lagrangians, UV Lagrangians, and test whether their EFTs match with regular gravity, with whatever is known experimentally, and then based on that, bring some candidates for UV Lagrangians that are interesting to work with. And I want to say something about how this started and the collaboration that's behind the scene, because during COVID we had those really cool Zoom meetings that emergent started going through different types of ideas, some of them touching on gravity, where people like Yaron, who we'll talk about later, and Eli, also Eli Kuflik and Yotam Sorek from High Energy Physics were participating with us in different meetings. Also students, Michael and Majed, Ron, Shimon, and Yoni Nilowski. Actually, that's how Alan joined us as well in this kind of pursuit. And it actually led us to pretty cool things. So I would say one is on the place where those kinds of ideas came from, of computational approach for science, is the project we call the Ramanujan machine. And Yaron will talk about this more. This is something that's now running for a couple of years and had pretty impressive success in math, in making discoveries based on a computational approach. But on the physics side, I actually took this concept and also applied to the Schmidt Foundation Schmidt Polymath Science Award is something we got just a few months ago to support this kind of effort. So we're now building an international collaboration with different people joining us to try to explore those kinds of ideas of a computational-driven effort in those kind of areas. And if you're interested, we'll be really glad to hear feedback from people here and to have people join us and play with us in these ideas. So, back to the talk, I want to say something about emergent gravity in more general terms. Because emergent gravity theories, it's a wide range of things done, right? And they go in very many different directions. We mentioned a few of them here. But the big difference with our approach is different in the sense that it's building on conventional quantum field theory. In a sense, it's much simpler. And it takes gravitational interaction also as arising for quantum field theory with just one or more interacting fields in flat space. That's basically where we want to bring it from.
Sakharov is also.
Yeah, right. It's a gravitational interaction arising from QFT. And in that there is a slight difference, because he's looking for gravity as arising. But it's worth discussing. It's not only one, and I'm bringing it as a positive thing, because what I think will be even more interesting is not just to try the one proposal I showed here, but to extend this computational approach and try to apply it to many more areas in emergent gravity. The challenge is that the tools right now are aiming for QFT. It will need to expand those tools even for non-QFT theories. But for some,
Sakharov also uses convention theory.
yeah, and that's good, right? From our side, it's an excellent thing, right? It means we can try to apply this approach for him as well, right? And something about the tools themselves. So what happened? Actually, the first one came out in December 2020 in arXiv, but then the publications were a little bit later. Those are recent developments. So there's 3 different groups, actually more than 3, that joined together, that wrote different tools for automating the calculation of diagrams for the purpose of effective field theory calculations. Those are all very recent. The one we kind of like the most is the one by Jose Santiago. He developed this thing he calls MME, or Matchmaker EFT, which is an acronym of an acronym, which is an automated 3-level and 1-loop matching of arbitrary models onto arbitrary EFTs. And it's still, well, it looks amazing, but it's still limited to 1 loop. So there is a lot of work to do if we want to push it even further. And it was so far never applied, none of them, to spin 2 fields. So no one actually tried to apply it for gravity. But that's, I guess, there is some work for us to do, and they're happy to pursue this now. And something about Matchmaker EFT, you can look it up online, but it's a really fun tool to download and play with. It doesn't have the most friendly interface, let's say. We can show more on this, but it's relatively friendly to use, and Alan can tell you more. But in not immense efforts, we managed to apply it on the Heisenberg-Euler Lagrangian, which they didn't try to do before. And for us, it was a good sanity check for the kind of ideas we were doing. So let me show you how it looks like when applying it there. Okay, just because I think it gives a bit of a feeling for this is the kind of output that you get from applying this computational tool. And I'm actually making it a little bit more friendly by splicing it in lines to different parts here. And still, what we actually have, and it's an output for this kind of search, right? This is getting the QED Lagrangian and asking what's the EFT after removing the electron-positron fields as a heavy particle. So staying only with the electromagnetic field. And what's happening here is that there is some intermediate calculation steps and then the final result. And let's step one further step into it. So what we actually have here is 3 parameters that we search over. Those are exactly the coefficients of the regular canonical kinetic term, and then those 2 additional terms that are candidates for the EFT. And then we're asking what they are. What we get is that we calculate it in orders. First, no loops, so you get nothing except for this 1 here for the kinetic term. And then there is 1 loop case, which you already get terms that look like they make sense, but there are still issues with renormalization. And then no loops after canonical normalization, which gives you almost nothing, and then 1 loop after canonical normalization. And then finally, when combining the results from the different contributions, what you get is this kind of creature. And you can see that it's the right thing by, well, noting a few things. One is that this is just a marker saying this is a 1 loop order, so it's not really changing the results. And then there is mu here that relates to renormalization energy scale. There is the mass of the electron, of course, that you see inside, and a few other constants. an epsilon bar that relates to renormalization, specifically dimensional renormalization. It's the 1 over epsilon there. So those basically give you the terms, and if you check the terms, those are exactly the ones that we need for Heisenberg-Euler. So it's a nice test. The method works, but of course now we need to apply it much broader, much wider, and we're working with them on making their tool relevant for spin-2. But I think there's a few questions that have been asked about it, and I want to touch on them because I think they are very important to understand what's the space of Lagrangians we want to search over. Right, this is a pretty important question to figure out. What's the space of Lagrangians that are even worth looking into? So here's an example term like this. Those are interaction terms between let's think about it as the perturbation of the curvature in a bit beyond free space, beyond flat space, and a scalar of some type. And we can put multiple scalars and even add interactions between those scalars. So there are quite a lot of things we can. But what do we test over? So here the idea is that the effective field theory Lagrangian of GR looks something like this. The first order that's relevant is this quadratic in H. Or this is giving us gravity waves, for example. And then there are additional higher order ones. So it's Taylor expansion around flat space. And then what we're actually looking for is a scenario like this. If there are normally terms that look like this, we want, for example, to replace them by an interaction of some type. But so the gravitons will not be directly interacting. That's an example that we can look into. And the next term, people worked on this many years ago, the next terms in this expansion will look something like this. And I think this is wonderful because it looks terrifying. And the fact that there are so many elements here it means that if we just try something random, we're probably not going to get exactly that. Right? So if we try enough things and one will precisely match to all the coefficients here, that will be a pretty powerful result. Right? That will be convincing in some sense. I think it's quite powerful. And if we get nothing, that's also fair. We can actually kill this idea or validate it in a fair way. Anyway, the final thing that is worth relating to is the most persistent question I get on this. And why is it even relevant given Weinberg-Witten? Because Weinberg-Witten have this famous work, an actual series of works, that gave an important theorem about ruling out emergent gravity. And the question is whether this is making our search futile. And the answer is no, but it does limit the space of UV Lagrangians worth enumerating over. And on this, we can say briefly that there is no point searching for diffeomorphism invariant UV theories. And that's, I think, the most common thing people do in EFT, actually. And there is no point doing this because, well, multiple reasons. But one is that this property will transfer to the EFT, and then it will automatically give us the lowest order GR. So we kind of discover nothing new. We'll not be able to validate that. And we also want to find the curvature as an emergent effect, which will be fundamentally different. And it also, once we give up diffeomorphism invariant in the UV, we'll hopefully get it in the EFT, we'll avoid some of the famous problems of quantum gravity, and we'll avoid many of the things that will limit us. But still, Weinberg-Witten is stronger than that. Weinberg-Witten is stronger than that. So we're going to look for UV theories without diffeomorphism invariance, such that their EFT will match with observed properties. But Weinberg-Witten still limits us here. And to understand exactly how to escape from Weinberg-Witten, I'll say we want to find ones that we can prove, and this is work that Alan was piling up together from different parts of literature, is that any UV QFT without diffeomorphism invariance must either violate Lorentz invariance, which is way worse in my opinion, or lead to massive gravitons in its EFT. And more precisely, I have just a little bit of time, more precisely, if you look at what is the actual condition for something to avoid diffeomorphism invariance, or for the EFT to be, but the UV not to be, then there are kind of three conditions. We need to break one of them at least. And what you can show by following on Weinberg-Witten, Weld, Herzberg, and Sandora, and some stuff by Feynman, how going from those conditions, you can actually get precisely to the fact that this is the kind of flow that I think I'll skip. But by a couple of different papers, you start from those conditions, and we very quickly get to diffeomorphism invariance. So we understand now that to build this space for Lagrangians, it will have to be a space that violates one of those. The one that I feel is the most interesting to try to break. The easiest as a test, at least, is the one about Newtonian attraction with unlimited range, which means basically going to massive gravity. And massive gravity is an interesting field on its own, but it's the easiest way for us to bypass all those rules limiting us. So if you want to search space, I think I'll just say briefly, massive gravity has a lot of interesting advances in recent years, partially due to LIGO. There are bounds that no one can read now, but on what's the minimal mass, what's the mass that the graviton can have. And I think it's quite interesting for us to try those types of gravity theories, but more broadly, we found out a few examples of what type of things we can do, except for massive gravity. And there are other types of EFTs that are interesting to explore. Some of them will require generalizing this code way beyond QFT. This is also worth doing, in my opinion. And with this, this is where we got with this research, and I'm really interested in hearing what people here think, and happy to also get feedback and discuss this further. I'll leave one slide with some of the pictures I showed along the way, so we can take questions on that. Thank you very much.
Thank you for a very informative talk. We have time for a few questions. So, yes.
Yes, is it on? Yeah. Sorry. It's a very interesting program, i.e. We have a lot of historical precedents like the W boson, right? The weak Fermi-weak interaction, and you pointed out the effective field theory, looking at the low energy part of that. So it's very interesting. The last part I missed out a little bit, which is when you introduce the massive graviton, you know very well that taking the massless limit of that does not give us massless graviton, which is, of course, what we know about graviton. Have you thought about that problem? For example, it has 5 degrees of freedom rather than 2, etc., etc.
And you mean by taking a massive one and taking it to zero? I'm not sure I
No, that's the thing, right? If you start up with massive graviton theory, it has 5 polarizations.
Right.
And there are famous theorems, Weinstein and so on, saying that if you take the massless limit of that, you don't get massless theory to begin with. So that's one thing you might need to...
because there will be additional polarizations to kind of avoid, or if you want to still match with
if
the
you really want the real massive, and behind that, of course, the philosophy of effective field theory in the way that you've been doing that, which I said I like very much.
Yeah.
Can we actually get to the bottom line? Or for example, the missing W boson, the analog of that. Would you be able to identify something like that to get to the full theory?
Yeah. So let me answer quickly on each question. On the first one of the other polarizations of the graviton that will emerge when taking the mass to zero, I believe that we'll be able to avoid those because we'll compare to an EFT that has multiple terms that are the ones we derive from reality, from what we know about regular gravity. And I believe that those additional terms will also help us avoid the other polarizations. If they don't, then those polarizations are consistent with nature, and then I would keep them. Right? I would want to have those candidates. So I believe that the terms we have in the EFT will help us avoid the physics we don't want.
Yeah. What about the W boson analog?
So there, I don't know. I think broader on EFT, on the computational approaches to EFT, also beyond gravity, it's definitely a method that should be applied more broadly. It's not super well known. It's pretty good. They developed it for a few other reasons that have to do with dark matter and other ideas, and studying SUSY theories and stuff like this. But I don't know whether they ever thought about it in this context. I'm not sure if it's a different program or if it connects to gravity as well. But I'll be glad to hear more on this.
Raise it to the brainstorming.
Next question.
Yeah, definitely. Thank you.
An effective field theory approach is, of course, always very valid. But for gravity, I'm not so sure what you are doing. Because a key element in effective field theories is, of course, that you keep the light particles. Now, we know the lightest particle. We have measured that we have a spin 2 particle. and it's essentially massless. After all, it with the speed of light to very high accuracy. I mean, this has been found observationally. So you have already 2 degrees of a massless tensor, essentially. And if you just stick with that, you cannot do without diffeomorphism symmetry. Because, I mean,
this is precisely the logic of Weinberg.
It actually goes much back earlier than Weinberg and Witten. I mean, it's a simple observation that if you want to have massless tensor fields and locality, you have to remove 3 degrees of freedom, 4 degrees of freedom, which are just, of course, the diffeomorphism degrees of freedom. Now, once you have, so you want now to have something where you start without diffeomorphism symmetry, but you have to start with a rather complicated theory. I mean, you know, the effective theory approach is you start with simple, you know, low energy degrees of freedom, and then you try to understand their interactions by additional heavy fields. Mm-hmm. But in this case, your low energy degrees of freedom should be already the massless graviton with diffeomorphism symmetry. Otherwise, you have already to start at low energies with a very complicated theory.
Yeah. So basically, the general issue here is that there are tens of years of research showing that there is barely anything we can do to get one gravity. That's the kind of disappointing thing. And still, there are so many holes and so many researchers in so many directions. So why do this? And I think, or maybe I should quote Gell-Mann again, in kind of trashing a bag of things to try to find something new. Because the naive answer should be something like this. Let's, for a moment, ignore all the rules telling us what we are not supposed to search for, and just run the code. And then, for example, what I expect to get is that we run the code, and we'll not be able to avoid, no matter what parameters we put in the UV Lagrangian, on how many fields, we'll always get a graviton with a mass that's not 0. That's one thing that those no-go theorems teach us, right? And now, if that mass, if we get a number that looks enormous, we'll say, okay, probably that's not a good theory. But if we get a natural number that is extremely small, and that happens naturally from the theory, I would say that this is a pretty cool coincidence, right? That maybe hints at something. If we get a natural number that is extremely small mass, and we get it naturally from the search, from some relatively simple user Lagrangians. Right. So I think in this sense, you should do a kind of suspension of this belief and say, if we try a large enough space, we'll see what mass we get. And if that mass is so small that it will still be consistent with actual experiments, then we have to consider it. If, on the other hand, this mass is enormous, then this thing dies. So at least we can kill it, which I think is an important thing about the theory and about our approach in general. But more generally, the reason we went into this approach through Weinberg-Witten is to exactly ask ourselves what is possible, right, and what's not. And there is still a hole we can go through. And that's a thing that's worth discussing further.
So, thank you. If there are any further questions, please have it in the coffee break. So now for